Welcome to section 3.3, part 2, where we're going to look at, the section is more logarithm rules, but we're going to be applying these to help us solve some problems using logarithms. So one of the problems that we've been dealing with, and we've talked about it several times, is that we are limited in what types of log problems we can solve. In a lot of the log problems, they've had to kind of set it up for us so that it's something we could do without using our calculators for a lot of problems. Mainly the main reason is the log x button you see on your calculator is with a specific base. It's a log base 10. So when we see log base 10, it's hard to write in something different than what you're saying. Yeah. When we see the log button on our calculator, this is actually the log base 10 of x. And the ln, of course, also we looked at, is another button on our calculator. It's specifically a log base e of x. And so unless our bases were lining up with those, we didn't really know how to deal with that. And this is where the change of base formula comes into play. We can find the log of any base, so we're just going to use b to represent that. Any random base, b cannot equal 1, a cannot equal 1. But for that, and if we did have some sort of button that was another one, a different log, you could do the same thing here. So this works with any base a. But since 10 and e are kind of focuses here, what we end up doing is just taking the log base of the same x, so whatever we're taking the log of, that's regardless of base, what goes on top there. And so we can, this would be your calculator buttons that we could use here for most of your calculators. And then we just have to turn around and divide it by the log of the base. So we see that base, that's what we divide it by. The ln, of course, is base e, the log button is base 10, or if you had something else, you could do it with any base. But this gives us the ability to electronically calculate the log. All right, so get your calculators out, and you can kind of check yourselves. We're going to do each one of these using those two buttons that you should have on your calculator, either the natural log or the common log. The natural log is the ln one, and the common log is just log base 10. So with log base 3 of 13, we can see 3 to what power gives me 13? Well, we know it's going to be somewhere between 2, which 3 squared gives me 9, and 3 cubed gives me 27. So we know it's going to be closer to 2 point something, but we can use our calculators to figure this out. Okay, so the log base 3 of 13, we could find by taking the log base 10 of 13 divided by the log of 3, the base. And doing that on our calculators, be sure to put that parentheses there. I'm doing it on myself here. Close the parentheses, in other words. You should get 2.33 approximately. And you can try that out. Take 3 to the 2.33 power, and you're going to get something really close to 13. The more we take those decimals out, it's 3.347, I guess, would be the other two, the closer it is to 13. I took it to the 3.3, so I took 3 to the 2.33, and we got something very close to 13, 12.93, right? So it's, it's not really 13. In fact, if we were rounding it to the 10th, it wouldn't even round it up. But if I took it to 3 to the 2.3347, putting that in there, 3347, oops, I forgot the decimal there. We'll just go ahead and insert a decimal. We get something definitely a lot closer, 12.9997. So even if I took it out to the tens, hundred, thousandth spot, that would round up to a 0, which would, round this up to a 13 eventually. Round this up to a 10, and then that 10 goes like this, and then like that. So by about the third or fourth place there, we get something that's obviously not exact because it's something that repeats forever, but it works. If we try doing this with the natural log ln, we can see a similar thing here. So log base 3, 13, would give me log ln 13 over ln 3. Plugging that into your calculator, you'll see that we get the same exact thing. So whatever base you're using, whether it's 10 or whether it's e, as long as you take the log of what we're taking and then divide it by the log of the base, we end up getting similar answers. So you have a choice there, right? With this problem here, we have two calculations we need to do. I would want to take the log of 9 over the log of 2 and subtract it with the log of 5 over the log of square root of 2. So putting those into your calculator, let's go ahead and do that. So we have the log of 9 divided by, and I'm having to close my parenthesis there. I don't know if you guys are noticing that, but when I enter in log, it opens a parenthesis for me to put in there. Got to close it so that when I hit divided by, you're not doing a long log there. We'll divide that by the log of 2. Close that parenthesis. This gives me 3.1699. And then we can do the second one there, log of 5 divided by the log of the square root of 2. Square root is above your squared button. If you haven't located that yet, I'm sure you have since we spent some time on that. And this gives me 4.643. 9, looks like. I'm taking it out to the same number of decimal places. So subtracting these two things, so 3.1, I'll have to clear this out, 3.1699 minus 4.6439, we get negative 1.474. So that is how we can use our calculators to actually do logarithms of any base that we choose. So this allows us to solve all kinds of different problems that we weren't able to do before using logarithms. And so we're going to look at just some examples of how we can use it. One is for exponential. One of the big things in exponents is growth or decay. And if we're using E, which we do in these couple formulas, we're looking at the natural growth and decay that we see naturally all around us, where AT is the amount after time t. A sub O, this would represent an initial amount in both of these, raised to the KT. The K will depend on the situation that we're in, but T is always time. And so K is something we need to find for anything. So it's our relative rate of growth is how it's defined. And then, or decay. When k is positive, which would be this situation here, then we have growth. If k is negative, as we see there with the negative k, then we have exponential decay. So they're showing that value negative, but we don't want to treat this like it's an actual formula. Here they're actually saying the k is negative, and so they're including that so we can say decay. But if you were to plug in a negative with that negative as your formula, that would actually make it positive, and then it's not decay anymore, it's growth. So it's a little bit different that they put that there. This is not a formula for exponential decay. It's simply saying that when k is negative, we have exponential decay. So do be aware of that. But k would be my rate of growth or decay. We also have a half-life formula, which is something that we use in science a lot for dating things, historical artifacts that we dig up or that type of thing. But half-life is something we notice in nature when we have radioactive items or items that are just naturally decaying, that they have a half-life where they slowly decompose over time. And the half-life is described as how long does it take for an item to be half of the quantity it was originally, so half of its initial value. The half-life h, so we're describing h as half-life, of a substance undergoing exponential decay at rate k. So because it's negative, we would have a negative down there, is given by the formula ln of 2 over k. Let's look at ways we can use these two formulas to do some calculations that involve logs. So let's look at how we can use the exponential decay formula to help us find the half-life of a substance. First, we need kind of an example. And in this experiment, we're given 18 grams of a radioactive element, sodium-24, that decays to 6 grams in 24 hours. Find its half-life to the nearest hour. All right, so we went from 18 to 6, so we know that that 24 hours is not its half-life because half of it would have been 9, right? But how can we find the half-life? First, we need to use the exponential decay formula, which we have on a couple slides back, right here. Keep in mind that we're not necessarily putting the negative in the formula, but we expect our outcome k to be negative. So using that formula, there we have it. We're going to put in the stuff that we're given here. And our t in this case, since we're talking about hours, is going to be done by hours, and they want our answer to be to the nearest hour. So we see that we started out with 18 grams, so that's our initial value here. T, time in this case, was 24. K, we don't know yet. That's going to be our rate of decay, and we just don't know it yet. And after 24 hours, we were left with 6 units. Okay, 6 grams, sorry. So we were specific enough there. The first thing we want to do is get the E, the base of my exponential equation, by itself. So we'll get rid of that 18 by dividing both sides by 18. 6 over 18 actually reduces down to 1/3. And that's E to the 24K. I'm going to write that with K written second. So the K, the value of the variable we want to solve for here in this case, is in the exponent. My goal is to get it out of the exponent, so I want to look at the base. Whatever I have as my base, and in this case it's an E, I want to take the log of the same base on both sides, because we know that the log base A of A to the x will be equal to x. So if I take the log with a similar base that I have, then I can take what's in that exponent and get it out of the exponent. Of course, I then want to take the log base E of both sides, which is ln. So I'm going to go ahead and do that. But had this been some other, base besides e, we would take the log of that base on both sides. All right, so rewriting this, I have the ln of 1/3 equal to 24k. My log base e of e just releases the exponent, and that's what I can have over here. And then solving for k is simply a matter of dividing both sides by 24. So k I find is equal to the ln of 1/3. Another way to write 1/3 would be 3 to the minus 1. And that actually allows us to take this out to the front as well. So that gives me negative ln of 3. That negative 1 just came out to the front. Got rid of it in the exponent over 24. This is my k value that I'm going to use to find the half-life. But my equation overall then for this problem, if I wanted to find the amount for any time t, would be a sub t equal to 18 times e to the negative ln of 3 over 24 times t. All right, so to find the half-life then, we're just going to come back to this formula and use the k value that we just found. H we know then is equal to the negative ln of 2 over my k value. Remember that my k value is negative ln of 3 over 24. So let's simplify this down a little bit if we can. So the ln of 2, we're going to think of that, as being in the numerator. We're going to multiply that by the denominator, which would be the reciprocal of the denominator, 24 over ln of 3. So writing this so that it's not a complex fraction, I would have 24 ln of 2 over the ln of 3. And we would want to do this into our calculators to see what we get for that. So doing that, you should get 15.14. Again, that's an estimation. We had to round it off to the second decimal place there. And so, and in our question, it said round it to the nearest hour. So it's approximately 15 hours is the half-life of sodium-24. So as we saw, sodium-24 has a pretty fast half-life, about 15 hours or so, a little bit more. Carbon-14 is something that all life is made up of, and it actually has a radioactive half-life of 5,700 years. And so this is a way that we actually will date a lot of dead items or things that have long passed away, to give an idea of how much or how long ago these organisms die. So as we figure out how much carbon is left in its thing, then we can see how dead or how long ago something has decayed. So we're going to use this to help us figure out how long ago King Tut's treasure has been sitting around. So in 1968, a group of specialists from the British Museum investigated whether a piece of art containing organic material found in King Tut's tomb, I'm not sure, you'll notice I skipped that because I don't want to mess it up, had been made during his reign, or whether it belonged to an earlier period. We know that King Tut died in 1346 BC and ruled Egypt for 10 years. What percent of the amount of carbon-14 originally contained in the object should be present in 1960 if the object was made during King Tut's reign. All right, so first, a couple of things we need to figure out. Let's take a look at our exponential decay formula. With the carbon dating, we know that the half-life is approximately 5,700 years. So I can put in for my time there 5,700 years, just like I did with the 24 hours in the previous problem. This is the amount I'm starting with, and so I know the amount that I want should be half of that. So let's go ahead and just put that in, 1/2 a sub o. And we're doing this basically so we can find k. So the amount is really irrelevant. Notice that I have that there. If I divide both sides here by that a of o, it actually disappears completely from my equation, which is great. So I have one less variable to deal with, right? And then I have e to the 5,700 k. We see the base is an e, so I'm going to take the ln of both sides here. So that gives me ln of 1/2 equals 5,700 k. And so solving for k, we can divide both sides by 5,700. And we get, again, k is equal to, this is the ln of 2 to the negative power, 5,700. That negative here can come out front then. And so I have k equals negative ln of 2 over 5,700. Doing the math there, we can find our value of k with a decimal approximation. Negative ln of 2 for many of you on your calculators, when you do this, you'll see 1.2160447 a long word, and then at the very end it says e minus 4. What this is scientific notation. And so the e tells you this is scientific notation. The negative 4 tells you, the negative will tell you we're going to move the decimal to the left. 1, 2, 3, 4. If the negative wasn't there, we'd have a positive large number, and we would move it 4 to the right. And then we put in zeros where there's blank spots there. And so we have negative 0.000. The number of zeros will always be one less than your number there. 1, 2, 1, 6. We'll just round it out. So we got 4 numbers there. It's to the 7th spot. But the more accurate we can bring that out, the more accurate my answer is going to be. And so this is my k value here. And so we can write out the formula for our carbon dating here. AT will equal a sub 0, e to the negative 0.0001216 t in the power. And this will allow us to take and find the age of any carbon thing. So looking back at our problem, the question dealt with this piece that was found in 1960, and we wanted to know, if it fell into the same age as King Tut's time period. And so we need to figure out what the time is, value that we want to plug in here. So t would be equal to 1960, and we're going to add that to the BC number of years, which would be 1346. And so that gives me a total of 3,306 years. And so now we would want to see how much of this carbon should be left. And so we can plug this in here and find the amount of 3,306 equal to a sub o of e to the negative 0.0001216 and 3,306 years. And we'll see what we get here. Working this out, you'll notice that I left the amount there. Well, we weren't given the amount of the carbon that we had, right? That what we're really going to look at is what's the result of this? What kind of number do we get? And I think you'll see here when we do this that gives us the answer that we're looking for. And what we see is I still have my a sub 0, but the outcome of this was 0.6636. Oh, I'm sorry, 0.66897. Have that wrong there. And so what does that tell me? Well, this is, if you think of this as just, the decimal, that's about 66.9% multiplied by a sub O, my initial amount. In other words, what we can say here with the carbon-14 dating is that the amount of my initial should be reduced by about 66.897% of the original amount, right? Of always means time. So when we multiply by these values here that are, decimals less than 1, we're actually getting a percentage. So the amount of the original carbon remaining in the object should be about 66.897% of the original amount. And if that's the case, then we have found something that did date back to the exact same time period as the original values, which would be in King Tut's time period. Now, King Tut began ruling Egypt 10 years before he died. So, if we want to know if the object they discovered actually falls into his time period, we would want to add about 10 years there from 1960 to 10 years before his death. So that'd be increasing that amount by about 10. And so plugging that in, I want to find the A of 3316 and see what kind of percentages we're talking about. A sub O E to the negative 0.001216 multiplied by 3316. Putting that in there, we get A sub O 0.66816. All right, so if it fell within that time period, we're going to see it fall somewhere between the amount of carbon being 66.816% and 66.897% of the original amount is within the time period of King Tut. And of course, this would be, these are approximations. But when it comes to carbon dating like this, we can actually get very, very, because carbon dating is a very, very exact process. This allows us to date these things within a pretty good small margin of error. So these are just a few ways in which we can use LN and our calculators to actually find solutions for things that normally would have been out of our reach because they were in the exponent of the function that we're trying to solve. So go ahead and practice this with our exercises, remembering that when you take the log of both sides, you simply need the log to match the base of which you need to get rid of for that particular problem. Thanks for listening to this, and we'll see you on the other side.